A barcode is an optical, machine-readable representation of data. The data usually describes something about the object that carries the barcode. Originally, barcodes systematically represented data by varying the widths and spacings of parallel lines, and may be referred to as linear or one-dimensional. Later two-dimensional codes were developed, using rectangles, dots, hexagons and other geometric patterns in 2 dimensions, usually called barcodes, although they do not use bars as such. Barcodes originally were scanned by special optical scanners called barcode readers. Later applications software became available for devices that could read images, such as smartphones with cameras. An early use of one type of barcode in an industrial context was sponsored by the Association of American Railroads in the late 1960s, developed by General Telephone and Electronics and called Cartrack. This scheme involved placing colored stripes in various combinations on steel plates which were affixed to the sides of railroad rolling stock. 2 plates were used per car, one on each side, with the arrangement of the colored stripes encoding information such as ownership, type of equipment, and identification number. The plates were read by a trackside scanner located, for instance, at the entrance to a classification yard, while the car was moving past. The project was abandoned after about 10 years because the system proved unreliable after long-term use. Barcodes became commercially successful when they were used to automate supermarket checkout systems, a task for which they have become almost universal. The use has spread to many other tasks that are generically referred to as automatic identification and data capture. The very first scanning of the now ubiquitous universal product code barcode was on a pack of Wrigley Company chewing gum in June 1974. Other systems have made inroads in the AIDC market, but the simplicity, universality and low cost of barcodes has limited the role of these other systems until technologies such as radio frequency identification became available after 2000. History. In 1948, Bernard Silver, a graduate student at Drexel Institute of Technology in Philadelphia, Pennsylvania, U.S., overheard the president of the local food chain, Food Fair, asking one of the deans to research a system to automatically read product information during checkout. Silver told his friend Norman Joseph Woodland about the request, and they started working on a variety of systems. The first working system used ultraviolet ink, but the ink faded too easily and was rather expensive. Convinced that the system was workable with further development, Woodland left Drexel, moved into his father's apartment in Florida, and continued working on the system. His next inspiration came from Morse code, and he formed his first barcode from sand on the beach. I just extended the dots and dashes downwards and made narrow lines and wide lines out of them. To read them, he adapted technology from optical soundtracks in movies, using a 500-watt incandescent light bulb shining through the paper onto an RCA 935 photomultiplier tube on the far side. He later decided that the system would work better if it were printed as a circle instead of a line, allowing it to be scanned in any direction. On the 20th of October 1949, Woodland and Silver filed a patent application for classifying apparatus and method, in which they described both the linear and bullseye printing patterns, as well as the mechanical and electronic systems needed to read the code. The patent was issued on the 7th of October 1952 as U.S. Patent 2,612,994. In 1951, Woodland moved to IBM and continually tried to interest IBM in developing the system. The company eventually commissioned a report on the idea, which concluded that it was both feasible and interesting, but that processing the resulting information would require equipment that was some time off in the future. IBM offered to buy the patent, but its offer was not high enough. Philco purchased the patent in 1962 and then sold it to RCA sometime later. Collins at Sylvania. During his time as an undergraduate, David E. Collins worked at the Pennsylvania Railroad and became aware of the need to automatically identify railroad cars. Immediately after receiving his master's degree from MIT in 1959, he started work at GTE Sylvania and began addressing the problem. He developed a system called CarTrack using blue and red reflective stripes attached to the side of the cars, encoding a 6-digit company identifier and a 4-digit car number. Light reflected off the stripes was fed into one of 2 photomultipliers, filtered for blue or red. The Boston and Maine Railroad tested the CarTrack system on the gravel cars in 1961. The tests continued until 1967, when the Association of American Railroads selected it as a standard automatic car identification across the entire North American fleet. The installations began on the 10th of October 1967. However, the economic downturn and rash of bankruptcies in the industry in the early 1970s greatly slowed the rollout, and it was not until 1974 that 95% of the fleet was labeled. To add to its woes, the system was found to be easily fooled by dirt in certain applications, which greatly affected accuracy. The R abandoned the system in the late 1970s, and it was not until the mid-1980s that they introduced a similar system, this time based on radio tags. The railway project had failed, but a toll bridge in New Jersey requested a similar system so that it could quickly scan for cars that had purchased a monthly pass. Then the U.S. Post Office requested a system to track trucks entering and leaving the facilities. These applications required special retroreflector labels. Finally, Calcan asked the Sylvania team for a simpler version which they could put on cases of pet food for inventory control. Computer Identics Corporation. In 1967, with the railway system maturing, Collins went to management looking for funding for a project to develop a black and white version of the code for other industries. They declined, saying that the railway project was large enough and they saw no need to branch out so quickly. Collins then quit Sylvania and formed the Computer Identics Corporation. As its first innovations, Computer Identics moved from using incandescent light bulbs in its systems, replacing them with helium neon lasers, and incorporated a mirror as well, making it capable of locating a barcode up to several feet in front of the scanner. This made the entire process much simpler and more reliable, and typically enabled these devices to deal with damaged labels as well, by recognizing and reading the intact portions. Computer Identics Corporation installed one of its first 2 scanning systems in the spring of 1969 at a General Motors factory in Flint, Michigan. The system was used to identify a dozen types of transmissions moving on an overhead conveyor from production to shipping. The other scanning system was installed at General Trading Company's distribution center in Carlstadt, New Jersey to direct shipments to the proper loading bay. Universal Product Code. In 1966, the National Association of Food Chains held a meeting on the idea of automated checkout systems. RCA, who had purchased the rights to the original Woodland patent, attended the meeting and initiated an internal project to develop a system based on the Bullseye code. The Kroger grocery chain volunteered to test it. In the mid-1970s, the NAFC established the Ad Hoc Committee for U.S. supermarkets on a uniform grocery product code to set guidelines for barcode development. In addition, it created a symbol selection subcommittee to help standardize the approach. In cooperation with consulting firm McKinsey & Co., they developed a standardized 11-digit code for identifying products. The committee then sent out a contract tender to develop a barcode system to print and read the code. The request went to Singer, National Cash Register, Litton Industries, RCA, Pitney Bowes, IBM and many others. A wide variety of barcode approaches were studied, including linear codes, RCA's bullseye concentric circle code, starburst patterns and others. In the spring of 1971, RCA demonstrated the bullseye code at another industry meeting. IBM executives at the meeting noticed the crowds at the RCA booth and immediately developed their own system. IBM marketing specialist Alec Jablonova remembered that the company still employed Woodland, and he established a new facility in North Carolina to lead development. In July 1972, RCA began an 18-month test in a Kroger store in Cincinnati. Barcodes were printed on small pieces of adhesive paper and attached by hand by store employees when they were adding price tags. The code proved to have a serious problem. The printers would sometimes smear ink, rendering the code unreadable in most orientations. However, a linear code, like the one being developed by Woodland at IBM, was printed in the direction of the stripes, so extra ink would simply make the code taller while remaining readable. So on the 3rd of April 1973, the IBM UPC was selected as the NAFC standard. IBM had designed 5 versions of UPC Symbology for future industry requirements. UPC A, B, C, D, and E, and C are installed a testbed system at Marsh's Supermarket in Troy, Ohio, near the factory that was producing the equipment. On the 26th of June 1974, Clyde Dawson pulled a 10-pack of Wrigley's Juicy Fruit gum out of his basket and it was scanned by Sharon Buchanan at 8:01 a.m. The pack of gum and the receipt are now on display in the Smithsonian Institution. It was the first commercial appearance of the UPC. In 1971, an IBM team was assembled for an intensive planning session, thrashing out 12 to 18 hours a day how the technology would be deployed and operate cohesively across the system, and scheduling a rollout plan. By 1973, the team were meeting with grocery manufacturers to introduce the symbol that would need to be printed on the packaging or labels of all of their products. There were no cost savings for a grocery to use it, unless at least 70% of the grocery's products had the barcode printed on the product by the manufacturer. IBM projected that 75% would be needed in 1975. Yet, although this was achieved, there were still scanning machines in fewer than 200 grocery stores by 1977. Economic studies conducted for the Grocery Industry Committee projected over $40 million in savings to the industry from scanning by the mid-1970s. Those numbers were not achieved in the time frame and some predicted the demise of barcode scanning. The usefulness of the barcode required the adoption of expensive scanners by critical massive retailers while manufacturers simultaneously adopted barcode labels. Neither wanted to move first and results were not promising for the first couple of years, with Business Week proclaiming the supermarket scanner that failed in a 1976 article. On the other hand, experience with barcode scanning in those stores revealed additional benefits. The details detailed sales information acquired by the new systems allowed greater responsiveness to customer habits, needs and preferences. This was reflected in the fact that about 5 weeks after installing barcode scanners, sales in grocery stores typically started climbing and eventually leveled off at a 10 to 12% increase in sales that never dropped off. There was also a 1 to 2% decrease in operating cost for those stores, and this enabled them to lower prices and thereby to increase market share. It was shown in the field that the return on investment for a barcode scanner was 41.5%. By 1980, 8,000 stores per year were converting. The global public launch of the barcode was greeted with minor skepticism from conspiracy theorists, who considered barcodes to be an intrusive surveillance technology, and from some Christians who thought the codes hid the number 666, representing the number of the beast. Television host Phil Donahue described barcodes as a corporate plot against consumers. Industrial adoption. In 1981, the United States Department of Defense adopted the use of Code 39 for marking all products sold to the United States military. This system, logistics applications of automated marking and reading symbols, is still used by DoD and is widely viewed as the catalyst for widespread adoption of barcoding in industrial uses. Barcodes such as the UPC have become a ubiquitous element of modern civilization, as evidenced by their enthusiastic adoption by stores around the world. Most items other than fresh produce from a grocery store now have UPC barcodes. This helps track items and also reduces instances of shoplifting involving price tag swapping, although shoplifters can now print their own barcodes. In addition, retail chain membership cards use barcodes to uniquely identify consumers, allowing for customized marketing and greater understanding of individual consumer shopping patterns. At the point of sale, shoppers can get product discounts or special marketing offers through the address or email address provided at registration. They are widely used in the healthcare and hospital settings, ranging from patient identification to creating SOAP notes with barcodes to medication management. They are also used to facilitate the separation and indexing of documents that have been imaged in batch scanning applications, track the organization of species in biology, and integrate within motion checkweighers to identify the item being weighed in a conveyor line for data collection. They can also be used to keep track of objects and people. They are used to keep track of rental cars, airline luggage, nuclear waste, registered mail, express mail and parcels. Barcoded tickets allow the holder to enter sports arenas, cinemas, theaters, fairgrounds, and transportation, and are used to record the arrival and departure of vehicles from rental facilities, etc. This can allow proprietors to identify duplicate or fraudulent tickets more easily. Barcodes are widely used in shop floor control applications software where employees can scan work orders and track the time spent on a job. Barcodes are also used in some kinds of non-contact 1D and 2D position sensors. A series of barcodes are used in some kinds of absolute 1D linear encoder. The barcodes are packed close enough together that the reader always has one or two barcodes in its field of view. As a kind of fiducial marker, the relative position of the barcode in the field of view of the reader gives incremental precise positioning, in some cases with sub-pixel resolution. The data decoded from the barcode gives the absolute course position, an address carpet, such as Howell's binary pattern, and the Inoto dot pattern is a 2D barcode designed so that a reader, even though only a tiny portion of the complete carpet is in the field of view of the reader, can find its absolute X, Y position and rotation in the carpet. Some 2D barcodes embed a hyperlink to a web page. A capable cell phone might be used to read the pattern and browse the linked website, which can help a shopper find the best price for an item in the vicinity. Since 2005, airlines use an IATA standard 2D barcode on boarding passes, and since 2008, 2D barcodes sent to mobile phones enable electronic boarding passes. Some applications for barcodes have fallen out of use. In the 1970s and 1980s, software source code was occasionally encoded in a barcode and printed on paper, and the 1991 Barcode Battle, a computer game system, used any standard barcode to generate combat statistics. In the 21st century, many artists have started using barcodes in art, such as Scott Blake's Barcode Jesus, as part of the postmodernism movement. Symbologies. The mapping between messages and barcodes is called a symbology. The specification of a symbology includes the encoding of the single digits, characters of the message, as well as the start and stop markers into bars and space. The size of the quiet zone required to be before and after the barcode, as well as the computation of a checksum. Linear symbologies can be classified mainly by two properties: continuous versus discrete. Characters in discrete symbologies are composed of n bars and n-1 spaces. There is an additional space between characters, but it does not convey information, and may be any width as long as it is not confused with the end of the code. Characters in continuous symbologies are composed of n bars and n spaces, and usually a but, with one character ending with a space and the next beginning with a bar, or vice versa. A special end pattern that has bars on both ends is required to end the code. 2 width versus many width. A 2 width, also called a binary barcode, contains bars and spaces of 2 widths, wide and narrow. The precise width of the wide bars and spaces is not critical. Typically it is permitted to be anywhere between 2 to 3 times the width of the narrow. Equivalence. Some other symbologies use bars of two different heights, or the presence or absence of bars. These are normally also considered binary barcodes. Bars and spaces in many width symbologies are all multiples of a basic width called the module. Most such codes use 4 widths of 1, 2, 3 and 4 modules. Some symbologies use interleaving. The first character is encoded using black bars of varying width. The second character is then encoded by varying the width of the white spaces between these bars. Thus, characters are encoded in pairs over the same section of the barcode. Interleave 2 of 5 is an example of this. Stacked symbologies repeat a given linear symbology vertically. The most common among the many 2D symbologies are matrix codes, which feature square dot-shaped modules arranged on a grid pattern. 2D symbologies also come in circular and other patterns and may employ steganography, hiding modules within an image. Linear symbologies are optimized for laser scanners, which sweep a light beam across the barcode in a straight line, reading a slice of the barcode light-dark patterns. Stacked symbologies are also optimized for laser scanning, with the laser making multiple passes across the barcode. In the 1990s, development of charge-coupled device images to read barcodes was pioneered by Well-Challen. Imaging does not require moving parts, as a laser scanner does. In 2007, linear imaging had begun to supplant laser scanning as the preferred scan engine for its performance and durability. 2D symbologies cannot be read by a laser, as there is typically no sweep pattern that can encompass the entire symbol. They must be scanned by an image-based scanner employing a CCD or other digital camera sensor technology. Scanners, the earliest and still the cheapest, Barcode scanners are built from a fixed light and a single photo sensor that is manually scrubbed across the barcode. Barcode scanners can be classified into three categories based on their connection to the computer. The older type is the RS-232 barcode scanner. This type requires special programming for transferring the input data to the application program. Keyboard interface scanners connect to a computer using a PS2 or a keyboard-compatible adapter cable. The barcode's data is sent to the computer as if it had been typed on the keyboard. Like the keyboard interface scanner, USB scanners are easy to install and do not need custom code for transferring input data to the application program. On PCs running Windows, the HID interface emulates the data merging action of a hardware keyboard wedge, and the scanner automatically behaves like an additional keyboard. Many phones are able to decode barcodes using the built-in camera as well. Google's mobile Android operating system uses both their own Google Goggles application of third-party barcode scanners like Scan. Nokia's Symbian operating system features a barcode scanner, while M-Barcode is a QR code reader for the MIMO operating system. In the Apple iOS, a barcode reader is not natively included, but more than 50 paid and free apps are available with both scanning capabilities and hard linking to URI with BlackBerry devices. The App World application can natively scan barcodes and load any recognized web URLs on the device's web browser. Windows Phone 7.5 is able to scan barcodes through the Bing searcher. However, these devices are not designed specifically for the capturing of barcodes. As a result, they do not decode nearly as quickly or accurately as a dedicated barcode scanner or portable data terminal. Quality control and verification. Barcode verification examines scannability and the quality of the barcode in comparison to industry standards and specifications. Barcode verifiers are primarily used by businesses that print and use barcodes. Any trading partner in the supply chain can test barcode quality. It is important to verify a barcode to ensure that any reader in the supply chain can successfully interpret a barcode with a low error rate. Retailers levy large penalties for non-compliant barcodes. These chargebacks can reduce a manufacturer's revenue by 2% to 10%. A barcode verifier works the way a reader does, but instead of simply decoding a barcode, a verifier performs a series of tests. For linear barcodes, these tests are edge determination, minimum reflectance, symbol contrast, minimum edge contrast, modulation, defects, decode, decodability. 2D matrix symbols look at the parameters symbol contrast, modulation, decode, unused error correction, fixed pattern damage, grid non-uniformity, axial non-uniformity. Depending on the parameter, each ANSI test is graded from 0.0 to 4.0, or given a pass or fail mark. Each grade is determined by analyzing the scan reflectance profile, an analog graph of a single scan line across the entire symbol. The lowest of the 8 grades is the scan grade, and the overall ISO symbol grade is the average of the individual scan grades. For most applications, a 2.5 is the minimum acceptable symbol grade. Compared with a reader, a verifier measures a barcode's optical characteristics to international and industry standards. The measurement must be repeatable and consistent. Doing so requires constant conditions such as distance, illumination angle, sensor angle, and verifier aperture. Based on the verification results, the production process can be adjusted to print higher quality barcodes that will scan down the supply chain. Barcode verifier standards. Barcode verifiers should comply with the ISO IEC 15426-1 or ISO IEC 15426-2. This standard defines the measuring accuracy of a barcode verifier. The current international barcode quality specification is ISO IEC 15416 and ISO IEC 15415. The European standard N1635 has been withdrawn and replaced by ISO IEC 15460. The original U.S. barcode quality specification was ANSI X 3.182. This standard defines the quality requirements for barcodes and matrix codes. As of 2011, the ISO workgroup JTC1SC31 was developing a direct part marking quality standard, ISO IEC TR 29158. International standards are available from the International Organization for Standardization. These standards are also available from a local, national standardization organizations, such as ANSI, BSI, DIN, NEN and others.